Thank you very much. And thanks to the organizers for the opportunity to meet with people again. I'm going to talk about Hagedorn phase transitions, and I'm going to tell you a little bit about the Bosonic BFSS model, but most of my talk, in fact, will focus on a Gaussian version, a Gaussian model, because it's closely related. So let me dive in, because I probably have very little time. So dimensional reduction of Yang-Mills on a torus. We take a D plus one dimensional Yang-Mills, dimensionally reduced by taking the zero volume limit of the theory on a D torus, you get matrix models. This is just a way of motivating them more than anything else, in that there's much more physics, obviously, and divergences and things like that associated with the real Yang-Mills theories. But if I reduce it, I'm retaining time, so we get a quantum mechanical model in the end, and it's a quantum mechanical matrix model. You see, there's one gauge field left. So the original Yang-Mills gauge field breaks up into a residual gauge field and some D n by n matrices. You can path integral quantize the residual model, and I've written out what it is here. The covariant derivatives, the commutator covariant derivatives, you're just left with commutator matrices, and you're left with the one covariant derivative here. So this written in this matrix model, and I've written it in its Euclidean form in a thermal bath at temperature T is equal to 1 over beta, and one can perform standard results on this. This is the Bosonic, what's called the Bosonic BFSS model, because it's related to other models. I'll get into that in a second. Just the residual gauge field, I've written it out here. And it is not dynamical. We're in one dimension, it can't be dynamical. But it does imply a Gauss law constraint. So the residual effect of it is it's really just a Lagrange multiplier. It gives you a Gauss law constraint. So if I go back to the Hamiltonian formulation, we can think of our partition function as the trace over physical states of e to the minus beta h. And I'm interested in rewriting this as a sum over energies with the degeneracy of the energies and e to the minus beta times e. And the main object of focus will actually be the degeneracy of states here. We want to understand what's going on with that. And physical means that the states that are considered are SU-in invariant. But first of all, we can get some idea of what's going on in this model just by very standard quantum mechanical variational techniques. You can put in an ansatz for your ground state wave function. Psi naught is take it to be a Gaussian with a variational parameter, and you can get an estimate for what the ground state energy is. E naught is 3d over 8, d minus 1 to the 1/3 is what comes out. I didn't go into the details. You can estimate there's a mass parameter that's playing a role in this, and you can estimate it by taking it is the lowest mass excitation of the ungauged model. It still plays a role in the gauged model, gives you some idea of what's going on, but it is not a physical mass in the theory. You can obtain it from the gauge model by taking a trace of this gauge invariant non-local object, where you connect the two different fields by a gauge transformation around the circle. And if you do some calculations with it and put in some particular assumptions, you can see that this one, it's the exponential fall off in this relation, and you can measure it on lattice simulations using that. But variational technique, you can get it just by forgetting about the gauge transformation, saying what's the lowest mass state of this correlator, and it is d minus 1 to the 1/3. So, so that's an older technique that's quite useful in understanding it. This model is to introduce an auxiliary field. I have expanded the matrix. I've only written the oops. I've expanded the matrix. I should have written out XA as being a matrices times TA. The generators of SUN are the matrices TA, and I've expanded them, and this is some coupling constant associated with the trace of 4 of those with commutators. And so you can see the structure of it, but you see that you have XA with 2 lower indices here, XB, XB. So it motivates putting in an auxiliary field, KAB, which you can integrate out, and you can rewrite the model in this fashion. This allows, so now we've got a KAB and we've got our XABs, and you can find a saddle point approximation for the KAB. Right? That leads to the 1/d expansion. But it's interesting to look just what is the representation content, first of all, of KAB, because it gives you a little bit more information on it. KAB is the symmetric tensor product of 2 adjoint representations. The symmetric tensor product of 2 adjoint representations always breaks up into a sum of 4 representations. It's actually simpler than you might expect. This was emphasized recently by Jens Hoppe. So there's some of it, and it has an identity, a singlet, and some higher representations, and the joint pops in, and some other representations that are higher dimensional. The 1/d expansion, what we learn from it is that the low energy physics is dominated by the singlet. Right? That the other ones, they are relevant to higher excitations, but they don't play a huge role in the physics at low temperatures and low energies. We can understand a lot about it from that. So the singlet, we put in an ansatz now for KB being dominated by a constant in that singlet. We get that KB is m squared times delta AB. Put it back in to this formula, and we get some constant here, and we're reduced to a gauge Gaussian model. So, and where m should be around d minus 1 to the 1/3. So the physics of this model should be dominated, in fact, by this particular Gaussian model. And the 1/d expansion, it's almost trivial model, but it still has it has this gauge constraint, which means that it's not really as solvable as you might think it is. And just the 1/d expansion, in contrast to the variational method, is valid at large d, and it gives this m to be d to the 1/3. So that's the setting. The model is closely related to supersymmetry extensions. One of the reasons for looking at it is because the models for membranes, this BMN model, it's a massive, if I said mu to 0 and I quench the fermions, then we get back this Bosonic BFSS model. If I look at this mu dependent one here and I take the large mu limit of it, it gives a supersymmetric gauge Gaussian model. And if you just focus on the fermions terms here, this term here, you see that you can describe fermionic Gaussian gauge Gaussian models, which are easier to study, but I won't go into those in this. They can give you additional information. The model is connected with many other ones, and one of the ones associated with QCD was studied by some of people associated with Bangalore. Sachin Vaidya here he's at the Institute of Physical Science. He's here in Bangalore. I probably get the institution wrong. And an overview of some of the related models is matrix membranes, BFSS model, etc. So but my main focus for the moment is, and I'll return to the BFSS model at the end, but I want to focus on the gauge Gaussian model. It is a model that has received attention in pure mathematics for a very different reason. They don't realize that they've studied it, but as is often the case, because they have other techniques. But so let me set up the context in the mathematics setting for you, because this may be a useful thing to do. So the Cayley-Hamilton theorem is a very basic theorem when we're dealing with matrices. It says that every finite rank square matrix X over a commutative ring satisfies its own characteristic equation. The characteristic equation is the polynomial, which is obtained by taking the determinant of the matrix minus X times the identity. And if I substitute the matrix into that polynomial equation, it says that the matrix, that P of X is 0. Those polynomials, you can construct them iteratively. That's a nice, just to so if I look for 2x2 matrices, you see that we can read off what the implication is. The equation that 2x2 matrices must satisfy is they must satisfy this algebraic equation. And it tells you that the trace of the matrix cubed is related to the products of traces of lower powers of the matrices. That's the key point for me. From 3x3 matrices, I've removed the trace because it becomes messy. You see that the product of the fourth power is related to powers of traces of matrices. And more generally, for any single matrix, you can replace the trace of X to the n plus 1 in terms of lower powers. That's the content of Cayley-Hamilton. And the result in mathematics as stated is that all matrix invariants are expressible in terms of this generating set, which is the trace of powers of the matrix up to the dimension of the matrix. And you get all the matrix invariants that way. Of course, the matrix invariants for a single matrix are just the eigenvalues, so you can re-express the eigenvalues in terms of the traces of the different powers. That's a nice classical problem. And the invariants of X are, they're of course the eigenvalues, but one can build, if one now says, well, how many invariants are there for a given matrix? As I take the number of products, how many states can I build is what I will work out. I'll come back to that in a second. You can build a partition function, which is the sum of the number of distinct invariants with t to the n, and this is just the number theory Pn of n, and it is the number of invariants formed from n x's. So, and P of n is the number of partitions of n less than n, and one can evaluate this particular sum. That's the partition function for this one. But now let's consider two or more matrices. That was the context. For two or more matrices, what happens if we consider, let's take a pair of them. The invariants are no longer the eigenvalues. However, the traces of products still provide the invariants for us. And in fact, all of the invariants can be that. So I've quoted some theorems in the mathematics literature, which is saying that there should be a longest chain of matrices, which is not irreducible. So the ultimate statement here is that the longest chain of matrices in capital N should be less than or n squared, and should be greater than, these should be capital N's, n times n plus 1 over 2. So it's sitting in this bound. So you never need matrices more than that. You need matrices, trains of matrices less than that. And the mathematicians have worked out some of these generating functions for two and more matrices. For two matrices, you can see that the generating function, you can read off from it. It tells you that I just need the trace of the matrix, the trace of one matrix, the trace of the second matrix, trace of the matrix squared, trace of a product of two matrices, and the trace of the second matrix squared. And it's generated freely, without anything. If I just expand this out, it'll tell you all of the invariants and how many of them there are. If I look at three matrices, you get something similar. However, you now have an additional constraint, T1, T2, T3. The term T1 indicates that three matrices X, Y, Z that we need to include this object, the trace of X, Y, Z, but we don't need to include its square. It satisfies a relation, but you do need to include that term. And if you expand this out here, the T is associated with trace of individual matrices. I'm going to skip this actually. So in general, this is the mathematics result. The problem of counting states with two matrices is in fact related to n equals, for n equals 4, Suzy-Yang-Mills, it's related to counting quarter BPS states. Oops, I'm going all over the place here. Yes, it's d equals 1 is counting one BPS, half BPS states, and d equals 2 is counting quarter BPS states. The dimensions of these objects have been evaluated for small n, for n equals 2 up to 6, and with two variables, that should be T1, T2, and for n equals 7 up to just one variable, T1, T2. And also we know that the large, if we take the large n limit of these ones, we get a product of these objects here, where, and you can see if I just take it for D matrices, T, it should go up to 1, but it has a pole, it develops a pole at first pole at 1 over D, T equals 1 over D. And that in fact is related to the Hagedorn transition. If I look at the dimensions of these coefficients, this is that entropic object that I was interested in. You see that it grows. We can see from this expression here, you can expand it out rather easily. This is d to the k times some t to some power. And if we work it out, you can see that if I divide by, for two matrices, I divide by 2 to the n, the coefficient of that dimension, it saturates at this, and this is a pure number which is related to the Euler function. But we see that this is the infinite n limit from that expansion written in that series sum, and this is what the full functions look like. They drop off exponentially. They will come up and come down, and those are the objects that would be of interest. So let me just describe them a little bit where this is coming from a Fock space point of view. From Fock space point of view, if I deal with that single matrix, we can deal with a matrix of creation operators. So matrix of creation operators, we can start with 0. We build new states, a new gauge invariant state is the trace of A dagger, trace of A dagger squared, trace squared of A dagger. These are all at level 2. And we sum them all up. The partition function is trace, and our variable t, we see there was occurring in the mathematics literature, is just e to the minus beta. So we have trace of our physical states of t to the n hat, where n hat is the number operator. So this is the partition function that we were looking at a minute ago. If we work it out, d equals 1, we can go back to our gauge Gaussian model, gauge fix, do our favorite trickery on it, and we can find it in this form, and we can perform the integrals and recover that expression. So summarizing that aspect of it from how the gauge Gaussian model, if you integrate out the x's, you are left with eigenvalues of that gauge field that we introduced with an effective action. The effective action is given by this quantity here, where I've written t's, and we introduce a different mass for each x to give the different parameters. So that will give us our gauge Gaussian partition for effective action. And this integral changing to complex coordinates is what's known as the Molien-Weyl Hilbert series. And it's the formula for the partition function. It's something we know. 5 minutes. Okay, I should go. For large n, from the physics of this, we can expand it out. It's going to be, if we expand out the t's, we can see that that it's going to be dominated at low temperature. When beta goes to infinity, the t's are much less than 1. We just keep the lowest one, and that gives what's called the A1 model in the literature. And the A1 model is just an integral over this gauge field, residual gauge field, times A1 trace and a trace of the inverse matrix. At high temperature, you can see the model just reduces again. That's our additional periodic time. We can reduce once more, and it reduces just a commutator, and we're left with an additional gauge field for A. And we can see what the large temperature behavior that the partition function goes as beta to the d minus 1 times n squared, and the dimension. If we read off what the dimensions look like, we see they should in fact go like this logarithm of n. So we can see that qualitative behavior dropping down from that. I'm just going to skip a little bit more on this. Because I'm running out of time. We can analyze this A1 model in more detail, and one can see how the coefficients are related to the finite inversions. And you see they again drop off. And the key point is going to be, if I look at the eigenvalue distribution, feed it back, you see the transition occurs at E is equal to 1/4, and that corresponds to an n is equal to n squared over 4. So this is the longest chain where trace relations are insignificant. They are insignificant up to the transition. The phase diagram for this model is the energy. I've plotted it here. If I scale the energy divided by n squared, it becomes 0 if I take a straightforward limit, and it jumps up to n squared over 4. The part that I was focusing in on is this red dashed line. What it means, if I go back to the implications for matrix models, we have found that the number of states grows as d to the n for n squared. So for small energies, so if I translate that back into the entropy as the log of this quantity, it goes as n squared log d, and the energy is E over n squared. The dimension from the other side, which one gets from the A1 model, and that Aharoni result, you can read off what the entropy is, that it has this behavior, and the transition occurs at energy at 1/4, where the entropy matches. So one can deduce. I'm just summarizing the result again here, since I'm running out of time. Let me show what that if I feed those entropy results back into the physics of the BFSS model, Bosonic BFSS model, one can compare with numerical simulations. So this is for 9 matrices, BFSS D equals 9, building from the entropy function, which you get from that gauge Gaussian model, taking that as a finite sum, you get the continuous curve. These are the simulations, how they fit it with n equals 24, lambda equals 40. And I've used the ground state energy because that's not part of that. So one should get that from elsewhere. For n equals 32, you see it fits perfectly. For n equals 48, again, the fit is essentially perfect. For n equals 65, the fit is, we're deviating up here because the Aharoni result is for the A1 model, not for the full BFSS model. One can see the same result if I just does the same thing for the for pure Gaussian model. So this is a simulation of n equals 65, d equals 9 for the BFSS model. Very detailed summary, and it fits to a very high precision the results coming from building the entropy precisely from the gauge Gaussian model. So that's the main point that I wanted to run down. The interesting thing that I wanted to highlight is that we are building the entropy from this. It's coming purely from trace relations becoming dominant in matrix models. The entropy at large n behaves as n squared over 4, and the entropy for black holes is a over 4. My feeling is that that quarter is not a coincidence, that it's that one can track the two of them and relate them, and that is related, should be related to gauge gravity duality, because these models have a gauge dual, have a gravity dual, and the gravity dual the transition occurs when it's the Hawking-Page transition. Yeah, I'm happy to discuss things. I've gone through it so quickly that I will leave it at that. I think I'm out of time. Okay.
We have a few minutes for questions if there are any.
So you are somehow from the bosonic BFSS and the Gaussian bosonic, motivating that there should be a scaling of the entropy as n squared over 4. And you're saying that black holes have the same kind of scaling, but bosonic BFSS does not have a gravity dual. Is it possible to do the same in supersymmetric?
In some sense, it presumably does have a gravity dual that we don't know, because you can consider it as a two-dimensional supersymmetric model, and you at finite temperature, and you consider a spatial circle as the one that corresponds to beta here. And in that case, if I consider it at high temperature, in that there's a known transition and a known dual in that case. If I squeeze down the temperature, the dual presumably still exists. It becomes less accessible, but it should still exist. I think it's just that you don't know what it is.
And what about supersymmetric BFSS? Can you apply this Gaussian also?
For the model, the statement is exact, and in fact, the A1 model covers the supersymmetric BFSS model in the large mu limit. If you go to large mu, you are in the large mu for the BFSS model, or the BMN model.
Yeah.
The BMN model, large mu, it becomes a Gaussian. And again, you can analyze it exactly the same way.
Okay.
And, the basic result is essentially the same.
Okay, yeah, thank you.
But I should emphasize that this result comes from the statement that at n squared over 4, trace relations become dominant. It is a model independent statement.
Yeah.
Yeah.
So connecting to Strato's question, you said that we can see the bosonic BFSS as something similar to the 2D model.
It's kind of it's a dimensional reduction where you kill the
Yes,
fermions.
But then you talked about dual, but you were talking about that in lower temperature range.
Sorry, in low.
I mean, by taking, we can have a dual to that 2D model.
You can have a dual to the 2D model, yes.
But the temperature range. So can we have that for that high temperature range, a dual?
You can look at the phase diagram of it and you can say, well, what's happening in the gravity side of that phase diagram? And I would say there should be a dual. You can then start arguing about the details of it. But
maybe for
yeah.
context, I showed that phase diagram of the 2D system in some of my lectures yesterday.
Okay, very good, yes.
Informing some of the questions here and showing that the functional form of the critical curve is known to be different in the low temperature holographic dual for the 2D 16 supercharged Yang mills compared to what you would get from the bosonic quantum mechanics in that high temperature limit, and how exactly those two different functional forms connect in this complicated, or as that holographic duality becomes more complicated or ceases to hold, is maybe the open question that we're
yes, the thing is that the question is gravity, are you in the weak gravity limit? And it's not obvious to me that you would be in that setting. Once you go to something like this, presumably you're not, and that may explain. Sorry, I expect that would explain the difference between those ones, because then the gravity side becomes not really useful to you. But I should see what you had to say in more detail.
We can continue discussing this. I'll
Sure.
do one last call for questions. We are just at the official end of time.
But maybe just one comment.
Yeah.
This quarter is incredibly robust, is the real point. And the robustness of it may be deceptive, is what I would say. That if the relation is simply that it's the trace relations become, that anytime you're dealing with a model that has matrices and trace relations become important at n squared over 4, and n squared is more or less the number of degrees of freedom. It's sort of related to your area. That quarter is going to come out naturally. So I would suspect that relation is more robust than other details.
Thanks, Denjoe. That sounds like a good point
Okay.
to conclude on. Let's thank Denjoe again.